Hi, myself Naveen Kumar Saini. In the course Wireless and Mobile Communication, code KEC 076. Today in the lecture 3, we will discuss about the multiplexing and the multiple access in the unit 3. So basically, what is the multiple access and what is the multiplexing and the multiple access? So in the one way we can say that multiple access is the advanced or you can evolved form of the multiple access, right? Or multiplexing. So multiplexing in which the multiple users send send or transmit the signals in by using the one channel, and at the receiver the demultiplexing will occur so that the all the other users can receive the same data which is transmitted by the different users. So in short, this multiplexing is a multiple users send the data into the given channel, right? So this technique by combining the different users data, right? So there are different ways of defining the same thing, right? Because as we said, it combines the data and using the one channel. So this channel which is used here, that is the L1 layer or the physical layer of the OSI layer, right? So there are some examples of this multiplexing techniques. So these are TDM, FDM, CDM and SDM. So these are the four basic or important multiplexing techniques which are used: time division multiplexing, frequency division multiplexing, and code division multiplexing, and the space division multiplexing. These are four types of multiplexing techniques are there. In the time division multiplexing, they have used the complete time frame is divided into the time slots, and each time slot is utilized by the different users. In the FDM, in the frequency division multiplexing, the different carriers are used to modulate the signals. Okay, so different channels are provided to the different users to send their own signals to on data. In the TDM, in the CDM, code division multiplexing, in which the different codes are allocated to the different users and then combine the signals by using the multiplexing. In the SDM, space division multiplexing, they are using the different directional antennas for receiving or for transmitting the signals, and it combine it and passing through the one channel. So this is a many to one, in short we can say, in which this many will be takes place with the help of TDM when we are providing the time slot, FDM when we are providing the channels, different channels, CDM when we are providing the different codes, and SDM when we are providing the different directional antennas. After collecting those signals or samples from the signals, by using all these methods, we combine it, multiplex it, and it transmit it through the channel. So multiple access, this multiple access are used to access the channels. Okay, so they are different access methodology for accessing the channels by the different users, which is based on some principle including the multiplexing as well. So we can say this multiplexing is the multiple access is the one step ahead of the multiplexing. So this allocates in the multiple access that allocates the different these channels to the different users, which also handles the situation when there are more messages which are available with the channels, right? So in that this is a way of accessing the different channels and by channels by the different users or access by the users. So these are the multiple access, and this multiple access schemes works on the data link layer, which is the L2 layer of the OSI model, right? And the examples for that is the TDMA, time division multiple access, FDMA, frequency division multiple access, CDMA, code division multiple access, OFDMA, the orthogonal frequency division multiple access, SC-OFDMA, single carrier orthogonal frequency division multiple access, and the space division multiple access. So there are different examples for the multiple access techniques. So in that for defining by using the multiple axis, we classify in the two ways. First one is the narrowband system, second one is the wideband system. So in the narrowband system, what they have in that system, with different channels are divided into the small band of that, and the signals are transmit using by small bands, and it is modulated from that band by small carriers and it is transmitted. So it means in the narrowband system we have a small bandwidth of by using by the different users. Okay, so narrow bandwidth systems, right? So that for that narrowband system, what is that the the in which the this carrier signal bandwidth, message signal bandwidth will be lesser than the coherence bandwidth. So this is the case when we are talking about the narrowband system. But in the opposite of that, in the wideband system, in which the channel bandwidth or even signal bandwidth will be greater than or more than the coherence bandwidth, or the larger than the coherence bandwidth. So this is the wideband system. So example of narrowband system is the flat fading concept occurs into it, and in the wideband system there is a frequency selective fading concept occurs into it, right? So in the last lecture we have discussed about the slow fading and the fast fading when we discuss about the fading concept, right? So these two are the example, this flat fading, which is the example of the narrowband, and the frequency selective fading, which is the example of the wideband system. So here we can just elaborate the things about the frequency division multiple axis. So how it looks like in the definition form. So we divide the bandwidth of the communication medium, which is the wideband right now. So we divide it into the different n overlapping frequency slots, and then assign a slot to each user, right? So if we have the band of you can say W band. So if we have this W band, we divided this different band the different frequencies like that, F1, F2 and up to Fn, and we allocate the F1 frequency or this frequency to the one user, second frequency to second user, third frequency to third user, and so on. Okay, then we combine this. After combination we multiplex it and we transmit it. So in this frequency division multiple axis, what they have done, we can see here, when we have the data from here, so this data will be multiplexed with the one of the frequency. So this is the one of the frequency. If I am saying this is the F1 frequency, so this data will be modulated with the F1 carrier frequency. Okay, similar to that in the data number 2. So this data number 2 is modulated with the second frequency. If I am saying this is the F2 frequency, and a third one, which is the silent things, which is maybe multiplied or the modulated with the third frequency F3, and the last 4. This is the example where the fourth this data segment 4 is multiplied with the F4 frequency, right? So this F1, F2, F3, F4, these frequencies, these frequencies are subcarriers, and these subcarriers modulates the different data streams, and we combine it into the channel, right? So we combine it. So this one is your F1, if you can see, this is your F2, this is F3, and this is the F4. So this F1, F2, F3, F4, these all are combined or multiplexed, and it is passing through the given common channel. Okay, so through this common channel we have multiplexed the signal, and this multiplex signal will be accessed by the different users. So this is one of the concept about the frequency division multiple axis. So there are some of the advantages and the disadvantages of when we are using the FDMA system, because this FDMA system was used in the 1G network, first generation networks, when this mobile communication come into the picture. So the advantages of this FDMA system is, first is it reduces the bit rate information, and then use of efficient codes increase the capacity as well, right? So it, and then very important point in this advantage of the FDMA system is that it reduces the ISI, inter-symbol interference, and the cost of the system will be reduced. So in the FDMA system, the equalization is not necessary, because this equalization is required when there is a ISI is more, right. So if the in the system the inter-symbol interference is more, in that case to mitigate this ISI we require the equalization. So this equalization is not necessary in the FDMA system because ISI is already reduced. So in that FDMA system, which can easily be implemented, right. So this is very easy to implement, and then that system can be configured so that the improvements in terms of the speed, speech encoder and the bit rate reduction, it may be easily increased, right, or incorporated. So in this way, this synchronization is transmission obviously it is a continuous in nature, less number of bits are required for synchronization. So this is very important feature of the FDMA system, where the ISI will be reduced, no equalization, means the complexity of the circuitry is not there, and then improvement of the system is occur when we are using a speech encoder, and the transmission is will be continuous and the less bits are required for the synchronization purposes. So some of the disadvantages also there in the case of FDMA system, it does not differ significantly from the analog systems, right. So it improving the capacity which depends on the signal to interference reduction or the signal to interference signal to noise ratio. Okay, so the maximum flow rate per channels is fixed, and the guard bands leads to the waste of the capacity, because when we have the different subcarriers, as I mentioned previously, the F1, F2, F3, F4 and so on. So between F1 and F2 we have to send the guard bands, right. So this guard band is not the informative things which we are required. So this guard band leads to a waste of the capacity, right, because we have the one fixed resource of the bandwidth and we are dividing into sub channels or the sub carriers. So we have the different there must be some gap between the two frequencies, right, F1 and F2. So this gap is obviously waste, because if we are using the gap of how much gap is there, more gap means more wastage of the bandwidth, less gap between the carrier frequencies, so less wastage of the bandwidth, right. Okay, so hardware implies the Narrowband filters in this case, and which cannot be realized in the VLSI, and therefore increases the cost as well. So it's very much cost effective. So in the FDMA system. So when we talk about the time division multiple access, so in that we divide the complete time period or the complete time slot or the frame into the different slots, right. In the FDMA we divided the complete bandwidth into the different bandwidths, and here in the TDMA system we divide the complete time into the small time, and we take the fixed amount of the frequencies or the common channel for that. So here when we use the entire bandwidth, right, so this entire bandwidth will be accessed by the different users in a particular time slot. So this is the multiple access. So here we have divided this complete time frame into the slots. So this is slot number 1, and this user 1 is sending this data by using the one of the set of the frequency. So this frequency is f only, right. So at this frequency this data is modulated and this is transmitted at the time slot 1, right. These are user 1. Now in the second case, when we have the data, so second user wants to send the data, so this data will be modulated by the same frequency, but this second slot is required for transmission of the signal. In the third case, when we user 3 wants to send the data, so for this purpose this user 3 will modulate the signal by the same frequency and it will transmit into the slot number 3. In the similar fashion, the slot number 4 will be utilized by the user number 4. So whatever data the different users have, so these users will modulate or use the bandwidth of the frequencies, same bandwidth of the frequency or the common bandwidth of the frequencies, and when they want to transmit, so they have to transmit by using the individual slots. So in one slot, one user will transmit the signals. In the second, as the one slot time period is over, the second user will use that slot, and that user will send the or transmit the data itself. Similar to that, in third slot, the third user will use that, access that slot, and they will send the data through that slot. In the similar fashion, fourth one, and so on. Then after this one, after combining all this modulated data and used by these time slots, they have specified in that into different time slots. So this is a time slot 1, time slot 2, 3 and 4. So these are combined, and this combined message will be transmitted into the system. Okay, so this is the one kind of the multiple access taken in the time division multiplexing. So some of the advantages of TDMA system and some of the disadvantages. Advantages are there. It permits the flexible rates where the several slots can be assigned to a user. So just for example, each time interval translates 32 kbps, right? So this 32 is the maximum voice signal which you want to transmit. So in this case, if you want to use, a user assigned it 264 kbps slots per frame. So when we will discuss about the frames, how these frames are divided into subframes and subframes are divided into slots and so on. So whenever we discuss about the LTE system, then in that case we will discuss in broad manner about the TDMA system as well. So it can withstand the gusty and variable bit rate traffic. So in that the slots which allocate to a user, it can be changed time by time or frame by frame, right? So just have mentioned that two slots in the frame 1 and 3 slots in the frame 2 and 1 slot in the frame 3 and the frame 0 in the slot 4. So in the of the notches for the slots 4. So in this way, this can be assigned the different, the use of the different slots in the by using the common channel. So there is no guard bands are required. This is one of the very important property of the TDMA system. No narrowband filters required for this case, because we are not we have the fixed common bandwidth, so we are not dividing the bandwidth. So we are using the same bandwidth, wide bandwidth or the wideband channel. So in that case, there is no need of required of the guard bands, and there is no requirement of the narrowband filter at the receiver, so that it can be received in the chunks, right? So it's not required here. So disadvantage for the TDMA system, which there is a very high data rates of the broadband system require for complex equalizations. Okay. Second is the due to the burst mode. So as I have mentioned as well, when you are when the second slot are used for transmitting the signal, so the previous frames which are in pending will be burst into that slot 2, right? If the user 2 wants to use a slot 2, so if the previous data is available with the user 2, then the burst of data will transmit through the user 2 as well. Okay, so it works in the burst mode. So large number of additional bits are required for the synchronization and supervision as well. So in TDMA system, this synchronization is one of the very important property which is required in the TDMA system at the transmitter and at the receiver as well. So electronics operating at high bit rates increases the energy consumptions, okay, because the circuitry is complex. So in that case, the high circuitry is required, and if we want to transmit the very high data rate, so in that case the complexity will be more and energy will be consumed more. Complex signals, which is complex signal processing, is required basically for synchronization within the short slots. So every slot have to be synchronized at the receiver as well. Code division multiple access. So this is also called the spread spectrum multiple access. Okay, so code division multiple access or the spread spectrum multiple access, in which we use the different pseudo codes when as we modulate the signals in the different TDMA FDMA systems by using the different carriers, we modulate this signal by using the codes. So in that the data bits, I mean these codes are applied bit by bit. So if we want to transmit the 1, so this 1 will be modulated by the different PN codes. Okay, so I am taking the example of the PN codes, right? So this is the pseudonoid codes. So these pseudonoid codes generations is there, which is used by the linear feedback shift registers, right? So which are used to, for generation of the PN codes. Okay, so every bit will be modulated by this PN code by applying the XOR operation. So what will happen? The spreading of the signal will occur. The bandwidth of the message signal will be spreaded. Okay, so this D1 into C1 is the simple fashion they have mentioned here, that each bit will be multiplied with the PN codes by the user 1. Similar to that, the user 2 will use the pseudo codes, second sequence of the pseudo codes, by which the every bit maybe 1s 1 0 like that. So each bit will be modulated or the multiplied with the core 2, right? In a similar fashion, when we have when the user 3 wants to transmit its own data, so in that case the another PN code is required for the particular user 3 to multiply with the D3, and this will be transmitted. So in that case, next is the user 4. So this user 4 wants to transmit the data bit. So this data bit will be multiplied with the another PN code. So all these 4 PN codes are required for the different users to transmit the data. And after I mean combining this data from user 1, 2, 3 and 4, so we combine this data and it is transmitted into the common channel. So this is, and that is why I am saying this is the one step ahead of the multiplexing in the multiple axes. So this is shown the D1 C1, D2 C2 plus D3 C3 and D4 C4. So it allows users to share the entire bandwidth simultaneously by use of the spread spectrum codes. Okay, so these are spread spectrum codes. Signals from the various users are separated at the receiver by the cross correlation of the received signal with each one of the possible user codes. So at the receiver side, the cross correlation of the received signal must be there, so that each user can identify its own data which is required, right? Dedicated data, right, for the particular user. So but as we have already discussed in the last lecture as well, that the PN codes must have the autocorrelation, right? So each bit of the PN code must have the autocorrelation, that is normalized to 1. So if the autocorrelation is maximum, then in that case it is very easy to detect at the receiver properly. So this is a representation of FDMA. So where the frequency is divided into the different bands, single bands, and here in TDMA system, each, I mean they are using the, these are in the frequency domain we had divided into subcarriers. In the time domain we are divided into the different slots. So these are the slots in which the data will be transmitted, and this data will be append with the guard time, right? So guard time will be added in that, and in each of the every slot, so that we can transmit the signal. In the TDMA system, we use all the complete bandwidth, and this bandwidth will be multiplied. I mean this in using this bandwidth, each code will be multiplied with the data bits, and the spreading of the signal bandwidth will be occur. So this is one of the property in CDMA system which is used, and spreading the signal bandwidth, and this is used to avoid the interception of the intruders or third party which wants to access the data. Okay, so and that is why the different more techniques are there, like the frequency hopping or time hopping. So these techniques are used to avoid some of the issues which occur in the direct sequence spread spectrum technique. So these all are used in the CDMA system. Another important point in CDMA system is they are using the cellular system only the one frequency, right? So every user will use the same frequency. So that is why this is the one cell cluster is there in CDMA system, where frequency reuse factor is 1. So in the one cluster, one cell is there, so each cell will have the same frequency. So some of the advantages of the CDMA system is there. So CDMA has a soft capacity, which is greater the number of codes, the more the number of users can be accommodated. So these advantages require a very tight power control, right? So it requires a very tight power control, because some of the issues which occur in the CDMA system is the near far effect. So due to the near far effect, how to control that near far effect? The solution for that one is the power control. Okay, and next, so it suffers from the near far effect. Okay, so in other words, a user near the base station transmitting with the same power will drawn the signal later, and all the signals must have the more or less equal power at the receiver. Fine. Second is the rack receiver. So this rack receivers can be used to improve the signal reception, which is delayed version of the time when it is transmitted by the different transmitted by the base station and it is receiving at the receiver. Okay, so in this case we can collect the signal and use to make the decision at the bit level. So as in the previous case, when we were discussing about the SSM, spread spectrum modulation technique, then at that time we have discussed that by using at the transmitter side we multiply the bits with the PN codes, and then we modulate with a different frequency, and at the receiver side again we multiply with the PN codes, and then we use the demodulation. For the demodulation again we use the different frequency as well, and then we use the then we receive the signal at the decision making device, and this decision making device is the threshold. For select the threshold, if value which is received above the threshold, then that is representing the logic 1. If value which is a signal value which is receiving lower than the threshold, in that case we see the logic 0 is observed at the receiver. So for that purpose the rack receiver is there in the CDMA system, which contains the correlators and the at the receiving side the correlators and the integrators, which are used to get the original message signal. So some of the disadvantages of the CDMA system is that time synchronization is required in the case of CDMA system, as some of the power required received and transmitted from the base station needs to constant tight power control, right? So this can result in the several handovers. So this is the very big disadvantage of the CDMA system, where the continuous MTSO has to check the handovers and the call termination will occur frequently. So this is one of the very big disadvantage of the CDMA system. So that is why the advancement of different evolution occurs in 1G, 2G, 3G and so on. So another very important point is multi-carrier modulation technique, in which when we have the band limited channel, so which cause always the inter-symbol interference. This is a very important point which must be keep in mind. So as I said, when we have the inter-symbol interference in any system, so to reduce that we have to require the equalizers, right? Then band, if we are using the band pass channel, so within a specified bandwidth, so this information bearing signal, it can be generated at the base band and then translated into the frequencies to the pass band of the signals of the channels. So this information signal is then transmitted through the channel and can be received at the receiver. So this is the second way of transmitting and reception of the signal. When we first is the band limited channel when we have, second option is when we have the band pass channel, okay, and third one is alternate approach is to have the to reduce its bandwidth, to design the system in that way the bandwidth limited or bandwidth efficient communication system may be can be obtained in the presence of the channel distortions, so which is equal to the ISI. So what is the procedure for that? So third approach is we simply divide the different one band of the frequency into the different chunks of the frequencies or the subcarriers of the frequencies. In that way, first thing is this, and second is we take out of the complete high I mean high length of the bits, we divide into small chunks of the bits, right? One blocks each block will have some specific number of bits, right? So each block will be modulated by the different frequencies. So if we have some length, so this length is divided into small lengths, so this length is nothing but the one block, different blocks, and these blocks are modulated by the different subcarriers. So this is the third approach which is used here. So for that one we have the OFDM system, in which so complete data stream may be 110 like that. So some data stream is there and we are taking the bunch of the different bit streams, right? So these bits stream will be converted into the parallelly, right? So if we have this data stream, so this data stream will be converted into the parallel stream. So this parallel stream is like, if this one is the M1, this is your M2 bit and M3 bit and so on. So these bits are modulated by the different frequencies and then combine it, and the resultant of this one is the OFDM signal, right? So this is the point of the multiplexing. So here itself it shows that when we have the frequency F1, frequency F2, frequency 3 and FC4, and this is the different this was in the frequency domain and the time domain. So when we combine all these four frequency signals, so after combining of the multiplexing, the signal which is transmitted, it will be like this one. So in the frequency domain, this when we combine all these four frequencies, then this resultant 0 to 4 frequencies will be combined and transmitted. So this is the example of the multiplexing as well. So it shows the combined effect of the different frequencies modulated signals which is needs to be combined. So it shows that again 4 subcarriers are required for, in the previous case it was a bit by bit, in this case we have the symbols. So in this OFDM modulator stage, what we have 3 symbols, S1, S2 and S3. So these 3 symbols are modulated with the frequency F1. Then these symbols S4, S5, S6, so this frequency is modulated with the frequency F2. And then S6, S7, 7, 8, 9, so this is modulated by the F3, and last is modulated by the F4. So all these frequencies, all these symbols, right? So these and what is this diagram representing? So this diagram is representing the constellation diagram of the different symbols. So this is representing into the time and the frequency domain. So this shows the different symbols which is modulated by the different frequencies, and after combining all these frequencies, so these symbols will be combined when we have the multi-carrier obviously, and we are using it. So after combining these frequencies or these symbols, this will be transmitted into the system. So it shows that what is the OFDM frame. So we can see here these frequencies, because we are talking about the OFDM. So in this the one frequency is completely divided into different frequency bands, F1, F2, F3, F4 and so on. So here we can see, so what is the representation, right? So if we are using the S1 to S1, S2, S3, so this S1, S2, S3 are using the frequency using frequency 1 to modulate. S4, S5, S6 is using the frequency F2, so this is using F1, this is using the F2, and the next S6, S7, S8, S9 using the frequency F3 for the modulation, and then F10, F11, F12, right? So this, this is the S10, S11, S12. So this is these symbols are using the frequency 4 for the modulation. So when we combine this complete frequency band, so we say this is the OFDM frame. So in one OFDM frame, how many symbols are there? We have the 4 symbols, but how many bits are there? There is a 12 bits are required for that, right? So S1, S2, S4 and so on are representing bits per symbol. So this is representing one of the symbol, and this one symbol of 3 bits are accommodated in that. So for that representation, so in the frame we have mentioned here, in one frame 12 bits are there. So in this we can also represent it when in the frequency domain, how to represent that S1, S2, S3. So this complete block is modulated by the frequency F1 and the resultant will be like this. Similar to that, S4, S5, S6, this is modulated by the F2 and the resultant will be like this. So this is a shifted version of the frequencies, so we can see here, right? So this is the shifted version of the frequencies. So different symbols are multiplied with the different frequencies and these are modulated, and so this shows the symbol OFDM symbol representation. So this is the OFDM symbol duration, that is a TS, and here is the OFDM frame. So it shows that the concept of the carrier frequency, which is allocation to the symbols. Okay, so this is one of the very important feature of the OFDM representation. So when we combine all this modulated signal, so these must be orthogonal in the nature, right? Because this is OFDM, so orthogonal frequency division multiple axis. So in that, this if you see these diagrams for the frequency F1, F2, F3, F4, so these frequency instants must be orthogonal to each other. Okay, so this theory is representing what is the meaning of this subcarriers representation. Okay, so in that I just want to keep your mind here that if I am talking about this one, so this how it is representing, so this representation must be like this. I will see if I have the diagram for that. Okay, so this must be like this. So if this one is my F1, so this must be F2, this must be F3, and the next must be the F4, right? So F4. So this, so there is a separation between these two frequencies, these two frequencies, these two frequencies. So these separations must be equal, right? Separation between the F1 and F2 must be equal. Second, the crossing of this for this curve must be the crossing must be here. So this must be the crossing, right? So in each section the crossing must be like that. There should not be any gap of the crossing. If there is a gap, it means there is a overlapping. So if there is no gap, it means there is no overlapping. So that is why this is orthogonal in nature. Dot product must be 0. So this is simply representing that TS is nothing but the n subcarriers, and T OFDM is the time duration for the OFDM system, which is used to reduce the ISI. So inter-symbol interference can be reduced in the OFDM system, and the SNR can be high. Okay, so SNR can be high, but there's some more issues are there in the OFDM system. We'll come into it. So in the implementation part, so we have the IDFT system and DFT system. So in which what is happening in the OFDM system, we are using the serial to parallel converter, and this then we apply the IDFT system, and after applying, there is an inverse discrete Fourier transform which convert into time domain, then D to A converter and pass it through the channel, and at the receiver side A to D converter, DFT is used, and then finally parallel to serial converter, and the estimated data which was observed here, it is receiving at the same time. Okay, so there is some of the very serious issues in the OFDM system. First one is very high peak to average power ratio, PAPR, right? So this PAPR issues occur when there is downlink signals. Okay, so when we want to transmit from the user to the base station, so in the uplink, so these issues occur very largely. So the solution for this one is a single carrier OFDM system. So in the downlink system we use the OFDM system, but in the uplink we use the SC OFDM system. So we can say the solution for this is the SC OFDM, where we use the spread DFT. That's it. So in the OFDM, when we are using the block diagram of OFDM, in that case we use the spread spectrum, spread DFT nature. So everything is mentioned here in diagram which I have just mentioned in the SC-FDMA system, where we use a M size FFT to reduce the ISI, and the uplink we use the SC-FDMA system. It is a representation. This is the main block which is representing here, which perform the endpoint DFT at the transmitting side. Okay, and at the receiving side we use the perform the endpoint IDFT system. So I hope this point is clear to all of you. This is the overall picture of the multiplexing and the multiple access. And thank you very much right now.